Hi guys, alright, let's talk a bit about operators, and I promised next video we're going to get onto some data. But let's just cover, this is probably the only other video I'm going to do about theory, and then the rest you're going to have to just talk to me on Zoom, okay? So let's just talk a little bit about the operators. You're going to need, there's only two relevant operators. So one is the projection operator. So we can see I've written, there's an equivalence of operators between the matrix form and ket form. Oops. Now, the key thing is, so this is a polarization operator at angle phi. So say I've got x and y. Let's just add some arbitrary angle phi. Okay. Now, if I'm in the phi basis, so this would be phi, and phi's perpendicular vector, okay? So this is the phi basis, just like how we had h basis and 45 basis, okay? This is how we write the polarization operator with kets and bras, ket phi, bra phi. And it's got to be that way, it can't be this way, because that just says the inner product of phi and phi, which is 1. This is not 1, okay? This is just a bra and a ket. No, a ket and a bra. We need to act on it, or have it act on some other state before it can become an operator, okay? So, let's start with the bra, ket bra interpretation, because it's a bit more intuitive. So, the idea is if we act, so operators act on a state and they give us another operator, okay? Sorry, another state. So say phi acts on phi. So I can write that. Phi, that's p phi, and then it's acting on phi. I get, this is 1, and I get phi, okay? So it stayed phi. So it acted on a state, and it got the same state at the end. That means that this state is an eigenvector of polarization operator. I'll make it the phi polarization operator. So phi is its eigenvector. Say it acts on h, p phi acts on h, equals phi h, okay? Now, that would depend on whatever h is in terms of the phi basis, okay? So this is like the projection onto phi. So let's consider something a bit more physical. Let's consider an expectation value. So you've gone through and you've seen that the expectation value of an operator here, hopefully you've read this, is the sum of the probability of a certain outcome times the outcome, okay? That's what the expectation value is, and we've seen that we can represent this sum of all possible outcomes, which have to be eigenvectors, right? And these are the eigenvalues times the probability of that outcome, or that eigenvector, okay? Coming out after the operator acts on it. And we can see that we can write that in this form, all right? So, what's the outcome here? What's the expectation value of the projection operator of phi, given that we're in the phi state? Okay, this is expectation value of this operator in the phi state. So we're measuring lots of ensembles of photons prepared in phi, and we're doing the projection operator, and we're taking the average. So just heaps of these. Now, as you can see, this is just going to be 1. Okay, so the probability, the average result is just going to be 1. Now, what does that mean? Gotten stuck. Right, so it essentially just means that every time if you send in all of these phi states, photons, and you do the measurement that corresponds to a phi projection operator, you measure all of them in phi, which sort of makes sense. So that the phi operator corresponds to a polarizer at angle phi. So it's you're sending through all these phi polarized photons, and you set your polarizer to phi degrees, then all of them are going to come through, okay? So, probably better to consider something a bit less general. So let's say we're in 45. Equals 102 H plus V. Okay, let's do pH. So we get expectation value of pH in 45 is this. Okay, so we can write that out. This dotted with V in a product with V and H is 0, so we just neglect them. Then we've got a H and H is 1, and a H and H is 1, and these two times together, so we get half. Alright, so the expectation value, we've got these 45. We've got all these 45 states coming in to our polarizer at H, and half of them on average come out. Okay, that's the point. That's what the polarization vector is doing, and it can be used to quantify outcomes, average outcomes from polarization measurements given an initial state, in this case 45, and for a certain measurement. Okay, so I think what I was trying to get at before is, so say I'm in the phi basis, and then I have to write it like this. Now, well, say I'm measuring along the phi axis, then I write it like this. But in matrix form, so I've got like a phi unit vector, if I'm going to write that in a matrix, and I've got a phi perpendicular, which was like from before, had some angle phi, and I had its perpendicular vector. Alright. So the idea is phi in matrix form is this. Operators are matrices and they act on states. And say I've got some numbers in the phi A and B. So this is the phi component and this is the phi perpendicular component, okay? So when I evaluate that, what do I get? I just get A. So it takes the phi component and then that gives me 0, and this one just takes the phi component. So it takes the phi component and it leaves it along that direction. That's what the projection operator does. So it projects your vector along whatever axes you want. It only takes the phi component and puts it there, okay? So same with HH, PH. In the HV basis, it's just a 1 here, 0, 0, 0. I've got a H component of little h, and I've got a vertical component of little v, and that's just going to give me h and 0, okay? So that's all well and good, but then you can also write this in another basis. So say I've got P45, right, which is just this in the 45 basis. But then I can convert that. So this would just be, you know, 1, 0, 0, 0, and plus 45 down there, okay? We're writing it in the 45 basis. So we've got 45, and we've got orthogonal to 45. And this is, sorry, HV 45, negative 45, okay? This video is going to be a long one. Apologies. Yeah, so now let's say we rewrite this so we can express 45 in terms of H and V, which we know already. 1 root 2. Half. So I'm doing the crab claw now. Okay. So, how do I write this in matrix form? So this is the same projection operator, but in the HV basis, right? I've converted that. It's kind of easy to do with Ketz and Bras, so that's useful. But now let's write this as a matrix. So, again, I've got my H component and my V component. But now I want P45 degrees, as in the projection operator of my polarizer being on the 45 degree axis. So whatever photon comes through is going to give me the probability of it being along that axis, a measurement along the 45 degree axis. So we've got a half out the front for all the vector components. But let's just remember that it's a half here, half here, half here, half here. All right, so this one projects some vector from H and puts it along H, okay? So this is the ket H, which means it's in the direction H. And this is going to act on a ket. So say I had H, so P45 acting on H, right? That's my initial state. This is going to give me 1, this part. And it's going to give me H here. So that would give me a H. So I need a 1. I need a 1 here. So if I had a H component, right, it's going to take that component and put it along H. That's what I want, okay? So take the H, this one, times like that. It takes my H and it's contributing to H, okay? Now, what about this one? So this one, from the H component, doesn't contribute. So I really just need to consider 2. I need to consider on V and H. So let's consider on V, so that gives me 0. So this is taking from, so I need to consider all the elements that are going to times this component that I get from here. So it acts on H, it takes the H component and puts that along H, okay? Now, the other one takes the V from there and puts that along H. So it takes V and puts it along H. So which element's that going to be? That's going to be this one, like that. Takes the V, this element takes V and puts it there. So again, I've got sorry, it shouldn't be 1s, I forgot my half, so that should be half as well, okay? Now, what about this one? This one takes H and puts it on V. So which one of these, is there one that takes H and puts it on V? Yep, this one takes from H. So if this acts on a H, I'm going to get 1 or a half and puts it on V. So I've got a half here. And then this acting on the V gives me a half and it puts it along V. So V and V, so that must be this one, so it's a half. So this is P45 in the HV basis in matrix form, okay? Hopefully that was illustrative. It was probably a bit confusing, but hopefully you can wrap your head around it. You can talk to me about it later. Now, the other video, sorry, what am I saying? The other operator is the polarization operator. Equals H. And I just want to explain what this is. With the single photons, you also do the double photon one, which is like HH plus, okay? You also do that one, and it's got 4 because it's higher dimension. So forget that for now. I'll just explain more about this one. So what are its possible outcomes? We need to find the eigenvalues. So PHV on H equals, let's just consider how this operator acts on a H state. Agree? That's 0. So I get H here, that's 1. So that's an eigenvector. H stayed as H with an eigenvalue of 1. So when I had this, the expectation value of some operator is the sum of probability. We haven't started looking at the expectation value yet, but we're going to. But this is the probability of a certain eigenvalue and times the eigenvalue. So one of the eigenvalues is +1, okay? And that corresponds to a vector, H, which is this omega vector. And this is the corresponding eigenvalue. So we know that one of these omegas is H, and its corresponding eigenvalue is 1, +1. How does PHV operate on V? Well, it gives you HV minus V equals negative 1 times V, okay? So that's another eigenvector, and the eigenvalue is 1. So V is an eigenvector, H is an eigenvector, and the eigenvalue is negative 1. So in the HV basis, both the orthogonal basis vectors are eigenvectors of this operator. All right. So let's consider what is the expectation value of this operator. So let's consider again a state. Let's consider H first. So expectation value requires an operator and a state. This is our operator, and the state we're going to consider is H, okay? So we do PHV, H. So what is the average of a polarization operator measurement, if it corresponds to some measurement, given an ensemble of H states? So all the H photons flying in, and we're doing this measurement. We don't really know what that is yet. And we have what's the average value of that measurement, okay? So H minus HV equals, they're both 0. This is just 1. So the average is 1. Okay, cool. Let's try the same thing with V. So now we're doing the expectation value, but with V, lots of V photons flying in. So now you may have already worked out what we're going to get. We're going to get an average of negative 1. Okay. Let's try 45. And we keep talking in the HV basis. So I'll write everything in terms of HV basis. So now I'm converting 45 to H and V, and I've put the polarization operator in the middle. That should all be in brackets. And 1√2 factor H plus V equals. So that's going to be 0. So the only ones that are going to survive are when they're both the same, because if I dot a H here, that's cool, but I need to dot a H here. If I dot the V, it's just going to all be 0 anyway. So this one only survives with the H and a H, so that's just going to give me a half. And the V only survives with the V and V, so that's just going to give me minus a half. So that equals 0. So the expectation of this operator in a H state is 1. The average in a V state is negative 1. The average in a plus 45 is 0. So essentially what this is doing is, let's just think about it. We're sending through all these H photons. The expectation value of this operator is going to give me plus 1 in the HV basis. If they're all V, I'm going to get a minus 1. And if they're half, which is the 45, I've got equal probability of H and V, it's going to give me 0. So essentially, the polarization operator, which is not the projection operator, which we did before, this operator doesn't correspond to a measurement, a physical measurement. You can actually go through and see that if you write this in matrix form, it does correspond to a certain matrix from the classical section. But that's coincidence. It's not a physical measurement. The matrix that it corresponds to, the physical optical device that it corresponds to, is not something that you can measure. Okay, you'll see what I mean if you go through and see what it is. It's impossible to measure what it does, which is a rotation. That's a hint. But what this does give you is a statistical tool. So if you get 1 in some state, it means that all your photons flying in were H. If you get a negative 1 as the expectation value, you're measuring some state and you don't know what it is, you're going to get a negative 1 contribution. And if you measure 0, you know that it was equal probabilities. So essentially what taking this operator does in an expectation value is to give you a statistical average of what your polarization incoming state is. Okay, and that's what we need to do for in 4 dimensions, except it won't anymore be an average. It won't be a measure of your average polarization. It'll be a measure of your correlations between the polarizations. So you'll need to go through and consolidate that and talk to me in the Zoom sessions. Cool, thanks.